Analytic semigroup. Analytic semigroups are another breed of semigroups as they allow for higher regularity of solutions. So in the end, you can show that the solution of a heat equation, for example, is smooth. There's C infinity. And this can be done using analytic semigroups. But the theory of analytic semigroups is also quite spicy because it digs really heavily into complex analysis. I'm not doing very much in this course. This is the end of the course. But I would like you to have seen this and also maybe appreciate a little bit the beauty, how complex analysis, operator theory, function analysis, how all this comes together in this section here. So let's jump right in with one of the major properties of complex analysis, which is the Cauchy integral formula. So we assume f is an analytic function in a domain, d of f in the complex plane. And then we consider a closed positively oriented curve, gamma, in the domain of definition. And we assume that the domain is convex. I didn't write this down, but I should. So that the curve is completely inside and doesn't go around poles or holes or anything of that sort. So in this case, then the path integral, the closed path integral, multiplied by 1 over 2 pi I of f of z divided by z minus a dz is equal to f of a. Or in other terms, this is the leading order term of the Laurent series of the function f of z divided by z minus a, where the leading pole is sitting at a. And now this is a formula we're going to use for operators in a second. But before I do this, though, I introduce something which is called a sectorial operator. And this has to do with a spectrum. So let's draw this out right away. So here's the complex plane. And I assume the spectrum is somewhere here. So it could have residual spectrum, point spectrum, continuous spectrum, all that kind of stuff. So let's say the spectrum of A is somewhere there. So ADA is called sectorial if there's an angle delta, so that the sector spanned by pi half plus delta lies in the resolvent set. This is the key property. The sector is entirely in the resolvent set. So let's draw this out. So I use an angle pi half plus delta, right? Pi half is 90 degrees, so I go a little bit further. This is the angle here. And then here I have the same angle, which is minus pi half minus delta. And now the sector is everything which is between or to the right of those two angles. So that's the sector pi half plus delta, except 0, right? I'm taking out a 0, so I usually draw this with a little arc here around 0 to make very clear that 0 is not part of it. But the rest is the sector, so everything to the right of this red line is the sector, and this all should be in the resolvent set. Basically meaning the spectrum should be outside of that thing. Okay. And now on this, I have an estimate that the resolvent is bounded by m epsilon divided by lambda for each sector which is just a tiny little bit smaller. So pi half plus delta minus epsilon. So let me draw this as well, maybe in black. So now I have a sector. Ooh, this is not good. Let's put this in blue or in green. How's my green? Green is too thick also. So let's plot this in blue. So this sector here has just an angle which is just a little bit less. It also excludes 0 and a little bit less. So then this would be for the sigma pi half plus delta minus epsilon. And so on a little bit smaller sector, we have a uniform estimate for the resolvent. But now if you get closer from the blue to the red, then this constant m epsilon might actually explode and go to infinity. Okay, so that's a lot to take in. So we have a complex plane, we have the spectrum somewhere on the left, and then we build a sector which is a little bit more than pi over 2. And all this should be in the resolvent set. Okay. So then we use Cauchy's representation of a semigroup. Let A dA be a densely defined sectorial operator with angle delta. And then we define an operator family T of Z as follows. So now we use the Cauchy integral formula right there. Bzzzt. Okay, so I take 1 over 2 pi I take a closed path integral over gamma of e to the mu z times mu I minus a to the minus 1 d mu. Or if you use our resolvent, we can write it as I divided by 2 pi, path integral of e to the mu z, resolvent mu a d mu. So far it's just a definition, but it will turn out actually that this defines our semigroup. Gamma is a piecewise smooth curve in this sector which we just defined, but it is using another angle. It is using an angle delta prime, which is between the argument of z and delta. And z is in a sector delta. Okay, so this needs another graph. So here was our definition of a sectorial operator. So this is sigma pi half plus delta. But now we go to a much smaller sector to define the semigroup. So we define it here in the red bit. So now this would be like a rather thin, you should imagine a rather thin cone around the real axis. So this would be then sigma delta. And in this sigma delta we define the curve, we define the semigroup. So then the z would be right in here. So lots of sectors going on. So the spectrum condition is a blue one, but the semigroup definition is only in the red bit here, just close to the real axis. Okay. So I wrote here, notice the level of strangeness in this definition. Because semigroups, we were looking at dependence of time, right? I was always arguing that t is like a time, a real variable. But now we are looking at a t of z. So this is a complex time. Well, it is not a complex time. It just says that this function t of t could be extended into the complex plane a little bit around the real axis, right? The real axis is part of the complex plane. So the interpretation of time is not lost, but mathematically as a function of t, it can be made into a function of z, where z is a complex variable, as soon as you are close to the real axis. It's a weird idea, I think, but it is actually a quite powerful idea as well. So that's it for today. In the next lecture then, I will talk about the semigroup properties which follow from the definition of a semigroup, which we did here through the Cauchy integral formula.